Hello everyone. In this video, we'll see a MATLAB program on autocorrelation of two discrete sequences. Before that, we'll know what is autocorrelation. So autocorrelation, it is a mathematical tool which is used to measure the similarity between a signal and a delayed version of itself. And here it will quantify how much a signal will resemble itself at different time lags or the shifts. So here this is the formula to find the autocorrelation of a sequence or two sequences, that is it is a signal and its delayed version of it. So here this k is nothing but the lag, okay, and rxx of k is the autocorrelation. X of n, it is a signal at any time n. So here we are taking the summation from n is equal to minus infinity to plus infinity. That is, we are taking the summation over the entire length of the signal. And this lag, it is maximum at this rxx of k, that is nothing but the autocorrelation. It is maximum when lag is equal to 0, and it is used to detect repeating patterns, then signal similarity and the periodicity. Now here in this program we are using the FFT in order to find the correlation. It may be autocorrelation or cross correlation. So what is the reason to use FFT to find out the autocorrelation? It is, here we use the FFT in order to find the correlation in general, because it will transform the correlation into a simple multiplication in frequency domain. So this will make the autocorrelation much faster, and it will be scalable for large data. So here we'll see this in detail. Suppose we are going for direct computation of the correlation. So here the formula for correlation, it is given by rxx of k is equal to summation x of n plus k. Now for a signal of length n, if we compute by using this formula, that is if we go by direct computation method, then for each lag, okay, for each lag k is nothing but the lag, there will be n number of multiplications. That is, we need up to n multiplications. So here there will be about 2n minus 1 lags, and the total complexity, it is O of n square. Okay, this O of n square, it is used to represent the time complexity. It is not total complexity, it is time complexity of any algorithm. So here for this the autocorrelation, calculation of autocorrelation, it will be very slow if the value of this n is very large. Okay, suppose we have the samples in millions in radar or communication signals. At that time, if we go for this method, it will take more time and the process will be very slow. So instead of this, what we do is we will go for the Fourier transform, that is connection to Fourier transform, that is fast Fourier transform. Here the autocorrelation is written as rxx of k is equal to x of n convolution x of minus n convolution x of n. So convolution with the time reversed copy. Okay. Now convolution theorem, it is given as Fourier transform of rxx of k, that is equal to magnitude of x of e raised to j omega square. So here this formula, it is called as Wiener-Khinchin theorem, and autocorrelation, it is the inverse of the Fourier transform of the squared magnitude of the signal's spectrum. So here this is nothing but the signal spectrum. Here the FFT algorithm, it will allow us to compute, that it is used to compute the discrete Fourier transform in only what? O of n log n operations instead of O of n square. So here the number of operations will be more, and here the number of operations will be less. Now we will go for the program. So here in our program, what we'll do is, first it will accept a discrete sequence from the user. Then it will compute the autocorrelation of the sequence using the fast Fourier transform method, that is the FFT method. Then in the third part, it will display the original sequence, its flipped version, and the autocorrelation result. Here we'll be giving the input sequence, that is user will enter the sequence to be analyzed, for which we want to find out the, or we want to compute the autocorrelation. Then we'll flip the sequence, and here the sequence it is flipped. Why? In order to prepare for convolution. Then we'll compute the fast Fourier transform, which is applied to both the sequences. Then we'll multiply the FFTs, that is the FFTs of the original and the flipped sequences. Then we compute the inverse Fourier transform in order to obtain the autocorrelation sequence. Then at last we'll display the results, and the results are displayed in the subplots. Now we will see the program. So here this is the program. I have divided this into two parts. So here CLC, clear, close all, these are commonly used for all the programs. It will be better if you use these all three in your program. So here CLC, it will clear the command window. Clear, it will clear all the workspace variables, and close all, it will close all the figure windows. After that, user will give the input. So here it we will be using x is equal to input, enter x. So here it will take a row vector. Okay, row vector from the user, that will be a discrete signal. So once this is done, we'll flip the signal by using y is equal to flip LR of x. So this flip LR, it will flip the sequence from left to right. Then we have nx, ny, and n. These all three, it will find out the lengths. So nx is equal to length of x, ny is equal to length of y. And this capital N, it is nothing but the total length which is required for the correlation. Next, we have to find out the fast Fourier transform, for which we'll use capital X is equal to FFT of small x comma n, capital Y is equal to FFT of small y comma n. You should be careful because this MATLAB is case sensitive. So here small x was our sequence, input sequence, and small y was our flipped sequence. Now we want to find out the Fourier transform of that, for which we are using capital X and capital Y. Okay, capital X is nothing but the Fourier transform of the what? Fast Fourier transform of the small x. Okay, that you should be very careful here. Then what we'll do? We will multiply these two in the frequency domain by using this equation, by using this command. So here it will multiply the two FFTs point-wise. Okay, so this will multiply the two FFTs point-wise. Then this is equivalent to the convolution in the time domain. So once this is done, we'll go for inverse fast Fourier transform for the to obtain the correlation. So we'll apply inverse fast Fourier transform here to get the autocorrelation result in the time domain. Then you need to display this autocorrelation sequence, autocorrelated sequence. Okay. Once we have done with finding all this, we'll plot the sequences. So subplot 3, 1, 3. This is nothing but we are using 3 rows, 1 column, and this will be placed in the first position. Okay, that is first position. Then next you have stem X. So stem, it is used to plot the discrete sequences. Then you have grid on. Then you have title, sequence of X. Color, we are using red. Okay, you can change the color also. You can use blue here, B. It will give blue color. You can use G. It will give green color. So these all, it will this is for the original sequence. This is for the flipped sequence. And this is for the autocorrelation sequence. And this is the flow chart. You can say this is a flow chart. This is similar to that of the figure which I've told you in the earlier slide. Okay. Here we'll enter the input as 1, 2, 3, 4. Here we'll be entering only one sequence. So it will get flipped when we use the command for y is equal to flip LR. then we'll get this as the output. Okay, so here this is for lag k. For lag k, you will be having the maximum value for the autocorrelated sequence here. Okay, then this is the output which you see when you execute the program in the MATLAB. Now here I have taken one example just to show the calculation of the autocorrelated sequence. So here the lag we are taking it as 0, 1, 2, 3, that is 4. Now we'll take a sequence x of n is equal to 1, 2, 3, 4. First we'll take the value of lag as -3. Here what we are taking, k is equal to 0, 1, 2, 3. We'll take on the left hand side also, that is -1, -2, -3. So when you put k is equal to -3 here, you will get this as x of n into x of n plus 3. Okay, x of n plus 3, like this you will get. So once that is done, you have to expand the equation. Okay, for for the value of 0, 1, 2, 3, that is x of 0 into x of 0 plus 3. Then next will be x of 1, x of n plus 1 plus 3, like that you have to expand, and you will get the value as 4. You have to substitute these values. This is x of 0, x of 1, x of 2, x of 3. So x of 1 value is 0, x of 2 is 2, then x of 3 is 3, sorry, x of 0 is 1, x of 1 is 2, x of 2 is 3, and x of 3 is 4. So you have to substitute these, and you will get these values, okay, which we have got in the previous one, that is in this figure. Here we got no 30, 4, 11, 20, 30, 20, 11, 4. So you can see these are the same values. So 4, 11, 20, 30, 20, 11, 4. Now here this is nothing but the autocorrelated sequence. These are the same values which you have got, and this is nothing but the value for the lag. So here this is just a visualization of the program what you have done here. So what you are doing is, we are taking the input sequence x, we are flipping that, we will get the sequence y. Then we'll find out the fast Fourier transform of x and fast Fourier transform of y. After that we'll multiply that. Okay, so here this is nothing but the pointwise multiplication. Once that is done, we'll find out the inverse Fourier transform. So for visualization, we are using sequence x plot. That is, we are plotting the sequence x, we are plotting the sequence y, and we are plotting the cross correlated sequence. Okay, now we'll see what are the benefits of using the autocorrelation. That is the practical benefits, why it is used. So here it is used because the efficiency is more. That is, there will be huge time savings for the large data sets. Okay, and second is the numerical stability, because this FFT, it is based FFT based autocorrelation. It will often match the PSD, that is the power spectral density calculations directly. And the applications are it is used in radar or sonar for echo detection, then wireless communication for synchronization and estimations. It is used in audio or speech for pitch detection. Then it is used for in image processing for pattern detection, and it is also used for like signal synchronization, feature extraction. Okay, so there are many applications. These are some of the applications for the autocorrelation, and this is just a pictorial representation of what we have done in this program. Okay, so signal in time domain, then FFT to frequency domain, then we have complex conjugate and multiplication. We have autocorrelation in time domain. So here the benefits are speed and the efficiency. Now we will execute the program. So here already I have typed the program in MATLAB. So this program, the same program which is in slide, same one. Now we'll run this. You will get enter x. So opening square bracket, 1 space 2 space 3 space 4. Closing square bracket. Enter. So here you'll get 1, 2, 3, 4. This is the output. Okay. You can see 4, 11, 20, 30, 20, 11, 4. And this is the figure. Okay, that is here. So this was the program about the autocorrelation of the two discrete sequences. Hope you have understood the program. Thank you.